va a ser dada en inglés, entonces voy a tratar de dar las instrucciones en ambos idiomas, ¿no? Por nuestros invitados. Entonces, thank you all for coming today to this lecture. Before we start, let me give you some important indications about the security of this, okay? Antes de iniciar, por favor, por protocolo, necesito dar estas importantes sesiones, estas indicaciones. If we need to evacuate this hall due to an emergency, it's very important to do with calm, no screaming, silent, without shouting, hitting, punching, kicking, no? Please, the others. So be calm, and it's very important to go out from this hall through the same doors you used to get in, no? So there is the emergency exits right there, and one more this place, okay? Thank you very much. En caso de alguna emergencia, por favor, hay que abandonar la sala a través de las mismas puertas por las que entraron. Tenemos otra aquí de emergencia. Hacerlo en calma, tranquilos, sin golpear, sin empujar, sin ¿verdad? Patear, etcétera, etcétera, al otro, ¿no? Con calma para que la tragedia no la hagamos nosotros. Bueno, muchas gracias. Vamos a comenzar. We are going to start introducing the people here at the table, at the front. First of all, we are going to present Doctora Catalina Morfín, Directora General Académica. Muchas gracias por venir. Nuestro director, Juan Carlos Martínez Alvarado, director del Departamento de Matemáticas y Física. Muchas gracias por venir. Our director. Our guest, Jerry Willinger. Thank you for coming. And Christopher Graney from Observatorio Vaticano. Observatorio Vaticano. We are going to start. Nosotros vamos a empezar con unas palabras de nuestro rector, el doctor Alexander Satirka, que no nos puede acompañar en este momento, pero dejó un mensaje grabado. We are going to start with some words from our dean, Dr. Alexander Satirka.
Hola, muy buenas tardes. Agradezco la invitación a inaugurar esta Semana de la Astronomía y saludo con alegría a todas las personas que nos acompañan. Me hubiera encantado estar con ustedes hoy, pero me encuentro de viaje. Pese a ello, no quise dejar de hacerme presente para decirles en nombre del ITESO, bienvenidos, bienvenidas. Me congratulo de que el estudio y la observación del universo sigan siendo temas presentes en el ITESO y que nos convoquen al encuentro, al diálogo y a la colaboración en este apasionante campo de estudio. Como universidad jesuita, nuestra institución forma parte de una tradición centenaria en la que el estudio y la enseñanza de las ciencias naturales es muy importante. Desde muy temprano en la historia de la Compañía de Jesús, nuestros antecesores se dieron cuenta de que para formar adecuadamente a las personas era necesario conocer la naturaleza e incorporar la física en los planes de estudio. Estoy hablando de principios del siglo XVII, cuando las ciencias naturales no eran parte de los programas académicos en todo el mundo y la ciencia moderna apenas nacía. Por esta razón, entre los científicos naturalistas se contabiliza a tantos jesuitas a lo largo de la historia. No solo astrónomos, que es el tema que nos convoca hoy, sino geólogos, meteorólogos, botánicos, arqueólogos y matemáticos, por mencionar algunos de los campos en que han contribuido a expandir el conocimiento. El temprano y especial quehacer de estos jesuitas permitió incorporar a la práctica de observar el mundo físico la de comparar lo observado con las teorías existentes para perfeccionar ambos procedimientos. Con ello se contribuyó a crear lo que ahora llamamos el método científico. Como reconocimiento de la comunidad científica mundial a su labor, 35 cráteres de la Luna y más de 30 asteroides tienen nombres de jesuitas destacados en los ámbitos de la astronomía, las matemáticas y la física. Entre ellos se incluyen 3 asteroides nombrados este mismo año por la Unión Astronómica Internacional. Vale la pena subrayar que el estudio de las ciencias naturales, tanto en el caso de estos jesuitas como a lo largo de la historia de la Compañía de Jesús, no ha sido un pasatiempo, sino una parte sustancial de su apostolado intelectual impulsado desde el gobierno de la orden. Esta labor conlleva el acompañar procesos de crecimiento y de transformación acorde con las personas, lugares y tiempos, según decía Ignacio de Loyola, que veía al apostolado intelectual como una parte central de la misión de los jesuitas. Esta opción fue refrendada en la Congregación General 34. El padre Adolfo Nicolás, en una carta que dirigió a la compañía cuando fue superior general, dice que el apostolado intelectual se manifiesta de manera concreta en una misión de investigar que nos permite ofrecer una aportación específica al desarrollo de la ciencia. Sin lugar a duda, el trabajo para comprender a la naturaleza y sus leyes propicia la admiración y reverencia por la creación, y en nuestra labor de acompañar en la formación integral de las personas. Hacemos un mejor servicio cuando estamos al nivel de la ciencia vigente que nuestro alumnado estudia. Conviene tener claro que para las personas que cuentan con una formación sólida, tanto en ciencias naturales como en religión, no hay un antagonismo entre ciencia y fe. Al contrario, la integración de ambas nos permite ubicarnos de manera más armónica en el mundo y en relación con nuestros semejantes. Esta larga tradición investigativa ha encontrado terreno fértil en el ITESO. A lo largo de su historia hay múltiples muestras de ello. En el tema que hoy nos reúne, encontramos que en 1957, el mismo año de su fundación, se ofreció un conjunto de cursos de extensión universitaria, entre los que se encontraba uno de astronomía. Esto fue incluso anterior a los primeros cursos académicos formales que impartieron en nuestra universidad, los cuales iniciaron en 1958. Desde entonces, el estudio de los fenómenos astronómicos ha estado ligado a la vida del ITESO. Durante los primeros 30 años de la universidad, se impartieron diversos cursos extracurriculares de astronomía y mecánica celeste. En tanto que para 1985 se instaló un pequeño observatorio ubicado en la zona poniente del campus. Ahí se ofrecían sesiones abiertas para la observación del universo, que se volvieron difíciles de continuar ante el avance de la iluminación artificial citadina, en la que ahora estamos inmersos y nos limita severamente en esta actividad. No obstante, el ánimo se mantiene, como lo demuestra el que desde 1995 se han impartido en forma continua cursos de astronomía optativos para todas las licenciaturas, que gozan de gran demanda, a lo que se suma la Semana de Astronomía ITESO, que se realiza desde el 2018. Esta breve reseña histórica, tanto de la tradición jesuita como del ITESO, sustentan una visión del sentido que tiene el estudio de la astronomía en nuestra universidad, así como las actividades para la observación y admiración del universo. Animo al equipo del Departamento de Matemáticas y Física, así como a las demás personas interesadas, a continuar con tan enriquecedora labor. Confío en que las diversas actividades que tienen programadas aumenten el interés de nuestra comunidad en estos temas y resulten en experiencias llenas de sentido. Muchas gracias.
ITESO, libres para transformar. Universidad Jesuita de Guadalajara.
Bueno, muchas gracias. A continuación, le damos la palabra a la doctora Catalina Morfín, que nos va a dar un mensaje muy importante.
Muchas gracias. Voy a acercar un poquito para acá porque me queda muy bien.
También lo podemos bajar.
Un poquito. Sí, no, ándale. Muchas gracias. Muy buenas tardes a todos y todas. Apreciados integrantes de la mesa de honor, querido Juan Carlos, estimados y distinguidos invitados Gerard Willinger y Chris Graney, we feel very honored to have you here. I hope this is not the last time and you come back soon. Queridas miembros de la comunidad universitaria, amigas y amigos todos. Como ya mencionaba el padre rector en su mensaje, la tradición astronómica en el ITESO es de larga data. No tengo la certeza, pero yo creo que ya desde la fundación de la universidad había personas interesadas en esta ciencia. Pienso, por ejemplo, en el padre Jorge Villalobos de la Compañía de Jesús, que en esa época era vicerrector y después rector de la universidad, que ciertamente se fascinaba con la física y seguramente se extasiaba al contemplar el cielo estrellado. Y lo mismo puedo decir del padre Luis Hernández Prieto, de la Compañía de Jesús también, por supuesto, alpinista de corazón, allá del CAIC, por aquellos que vienen del CAIC, fundador del ITESO y creador de la carrera de Ingeniería Química. El caso es que muchas personas de esta comunidad han estado entusiasmadas permanentemente por conocer la aún misteriosa vida del universo que nos rodea. No me detengo en la larga tradición jesuita en relación con la astronomía. Basta con apuntar que 35 cráteres lunares llevan el nombre de los jesuitas y que en este momento, en unos momentos más, Chris Graney nos ilustrará sobre cómo los jesuitas estuvieron girando literalmente alrededor de la rotación de la Tierra. Les quiero compartir ahora una frase de la autobiografía de San Ignacio de Loyola, fundador de los jesuitas, para hacer junto con ustedes dos breves reflexiones. San Ignacio decía en su autobiografía: era mi gran consolación contemplar el cielo y las estrellas, lo que hacía muy a menudo y por tiempo prolongado. Y al hacerlo, sentía una llamada urgente a servir al Señor. La primera reflexión es la siguiente. A pesar de la dificultad que hoy tenemos para contemplar las estrellas, pues casi no las vemos por la gran cantidad de luminarias que tienen las ciudades, todavía podemos consolarnos al detenerlos a observar el cielo. Y con consolación me refiero al significado que le da a esa palabra el mismo San Ignacio en sus ejercicios espirituales, aunque ahora la traduzco en términos laicos y no religiosos. La consolación sucede cuando me inflamo en amor, cuando a diferencia de estar eufórico, experimento una alegría interna, un aumento de fe en mí mismo y en los demás, un aumento de esperanza en la realidad y un aumento de amor por el mundo. La consolación, por otra parte, lejos del relajamiento que trae, por ejemplo, un masaje de spa, nos regala una paz honda y un equilibrio difíciles de conseguir por nuestros propios medios. Es el momento en el cual podemos percibir de cerca el vínculo que nos une al universo y a las demás personas. Es cuando la realidad herida, la personalidad del mundo, se nos presenta como una posibilidad de transformación porque somos conscientes del valor de la criatura. Así pues, creo que en esta semana de astronomía se nos abre no solo la posibilidad de contemplar los cielos y las estrellas, sino también de afianzarnos en la confianza en que este mundo puede mejorar si le ponemos una pizca de esperanza y también de amor, es decir, de consolarnos al ver que hay algo más allá de la violencia, la inseguridad, la desconfianza, y que hay algo más que mis heridas y conflictos personales, pues el universo en su inmensidad contiene mucho más que estas desgracias. La segunda reflexión es sentir esa llamada urgente a servir que sentía San Ignacio al contemplar el cielo y las estrellas. Creo que en general, al estar solo al ras de la tierra, podemos caer en la tentación de que estamos en medio de una situación sin salida, sin remedio alguno. Es cierto, quizá no podamos encontrar un remedio absoluto a los aconteceres de nuestra historia, pero bien que podemos encontrar algunos remedios. Uno de ellos es, con certeza, la disposición a servir. Esa disponibilidad para servir a otros no es fácil de alcanzar, pues estamos en un mundo que nos empuja ya sea a encerrarnos a nosotros mismos o a buscar, antes que nada, nuestra propia satisfacción. ¿En dónde podríamos encontrar el llamado a servir? Muy difícil saberlo, pero sí podemos decir que cuando nos dejamos llevar por esa gran aventura que es la evolución y el destino del universo, además de encontrarnos a nosotros mismos, también encontramos nuestros vínculos con los demás y por lo mismo percibimos nuestra pequeñez y al mismo tiempo captamos nuestra grandeza. Me faltan las palabras para expresar algo más y recurro por ello a un ejemplo poético. Es de la autoría de un jesuita, Gerard Manley Hopkins, que a pesar de vivir en una gran depresión profunda, decía: mira las estrellas, mira arriba hacia el cielo, o mira ese pueblo de fuego posándose en el aire, las villas luminosas, las ciudades circulares. Cierro comillas. Que estos sean los frutos de esta Semana Santa, de esta Semana de Astronomía, mirar el cielo sabiendo que aquí en la tierra pueden florecer y brillar por sí mismos los seres humanos. Muchas gracias y que disfruten mucho esta semana.
Bueno, pues vamos a presentar a nuestro invitado. Christopher M. Graney is an astronomer and a historian of science who also works in public relations for the Specola Vaticana, or Vatican Observatory, at the Vatican City State at the Vatican Observatory Foundation in the US. His research focused primarily on early telescopic observations of stars and secondarily on the broader work of astronomers of the Society of Jesus who made such observations. This work has led to books with the University of Notre Dame Press, one of them setting aside all authority, Giovanni Battista Riccioli, and the Science Against Copernicus in the Age of Galileo, and the other, and mathematical disquisitions. The booklet of this immortalized by Galileo. Also, Christopher Graney has numerous papers on journals such as the Journal for the History of Astronomy, Scientific American Physics Today, and the Catholic Historical Review. Most recently, Graney and brother Guy Consolmagno, director of the Vatican Observatory, have written When Science Goes Wrong, The Desire and Search of the Truth, just published by Paulis Press. So, having introduced our guest speaker, let us begin with the inaugural lecture. Welcome, Christopher. Thank you, and please give him a round of applause.
Muchas gracias. I hope that maybe in the future, if I am back, I will be able to do more in Spanish than say muchas gracias. But I can read a little, I can understand a little, I can speak nothing. So, a couple of introductory remarks. Got it? Yeah, good, thank you. First of all, I am not a Jesuit, but I do work at the Vatican Observatory. Closer? Like this. Okay.
Do you want another microphone?
That will be fine too.
Okay.
Okay, so anyhow, while he's doing that, I'm not a Jesuit, but I work with the Vatican Observatory, which has 2 locations, one in Rome, or just south of Rome, at Castel Gandolfo, which is a large chunk of Vatican territory on top of a volcano, now most of the people at the Vatican Observatory are Jesuits, and one of the Jesuits, Brother Bob Mackey, is currently involved with the OSIRIS-REx mission, which has returned the sample from the asteroid Bennu to Earth. And Brother Bob Mackey measures the properties of meteorites and asteroids, and he uses a laser scanner, in part, to help determine volumes of these small bits of rock. And so he likes to say that he has, in his laboratory, and he likes to say that he has a laboratory with a laser on the rim of a volcano. So what better mad scientist thing could you have than a laboratory on a volcano with a laser? So, here we go. Okay. Okay. Then, I think that one worked better. So then, the observatory the observatory's telescopes were originally in the Vatican itself, and you'll see some pictures of that. It moved to Castel Gandolfo in the 1930s because of the problem of waste artificial light illuminating the sky. Okay, artificial light is not a bad thing, but it does no good, and it wastes money and produces carbon emissions if it just goes up into the sky. Eventually, the lighting got so bad, even at Castel Gandolfo, that the observatory needed a dark sky site and ended up building a telescope on a mountain in Arizona on Mount Graham. And so the other site of the observatory is in Tucson, Arizona. So technically, the Italian side is the Vatican Observatory, and the operation that runs the North American side is the Vatican Observatory Foundation. And I'm sort of tied in with both. And now, since I've been silly enough with the microphones, we will begin. What I'm going to talk about is the work of the research by me and Brother Guy Consamagno. This story is published all very recently. So if you have not heard of this, it's because it wasn't around to be heard of more than a couple years ago. It's in When Science Goes Wrong. This book just came out in this month, in October. It came out, we had a more scholarly version, so the story about the Coriolis effect makes up a chapter in When Science Goes Wrong. A more scholarly discussion in the Catholic Historical Review for spring of 2023, and also an article in Physics Today, Wide of the Mark by 100 Yards, Textbooks and the Falklands Coriolis Myth, and that's in 2022. Okay, so what is the Coriolis effect? The Coriolis effect is something that comes from from being on any rotating object, or what we would call in physics a rotating frame of reference. Now, on the right, you see someone on a carousel rolling a ball. The carousel is rotating, okay? The ball, if you looked from above, would travel in a straight line after the woman rolls it, but because she is going around the carousel, okay, the ball returns to her. So you could imagine she sends the ball this way, and she's going this way, so she sends it, and then she comes around over here and is on the other side by the time the ball gets to the other side of the carousel. And so therefore you get this appearance. If you put the camera on the carousel, the ball seems to curve. On the Earth, we imagine if we have a rotating Earth and we shot a projectile down from the North Pole to the equator, right? The projectile would travel in a straight line as viewed from the stars, or a curve around the Earth as viewed from the stars. But on the Earth, because the Earth is turning underneath that projectile, the ball would appear to have a curved path. So, thinking about this projectile, okay, the black line is the path that is seen both on the Earth and from the stars if the Earth does not spin. If the Earth does not spin and we shoot a ball to the south, we expect it just goes south, nothing else. The blue line is the path seen from the stars if the Earth is spinning. You shoot the ball to the south, and it goes to the south as seen from the stars. But the red line is the path seen on the surface of the Earth, because as the ball travels to the south, the Earth turns underneath it. And so you get this curving shape that is caused by, that's the Coriolis effect. Now, take that and imagine, now where to put the laser, here. So we see this shape here. Now, imagine wind. You have a low pressure area, a strong low pressure area here. Wind comes toward the south, from the north to the south, toward the low pressure area. But because of the turning of the Earth, it will deflect like this, and so it deflects this way. If you shot a projectile in the other direction from the equator north, the effect goes in the opposite direction, because on the equator you are moving to the east rapidly. So here you're moving fast, and here you're not moving at all. So if you shoot a ball this way, it's being carried this way by the Earth's motion faster than the ground that it gets to. So it goes that way. So air coming up goes that way. And then this also works, it's more complicated, but it actually works in all directions equally. And so in each case, the deflection is to the right. And you produce a rotation, and then that is what causes rotation around a low pressure zone. And in extreme cases, that is why you have hurricanes. Okay? If you look on Jupiter, Jupiter is a very rapidly rotating planet, okay? And it is full of swirls and storms and air churning around, okay? In large part from the Coriolis effect. If you look at Venus, Venus is a very slow rotating planet, and it has no swirls in its atmosphere, okay? From the no stormy looking things, no spirals. So the Coriolis effect is what's behind hurricanes. Now, there's a lot of interesting stories about the Coriolis effect. One is that the Coriolis effect is what makes water swirl down drains. Okay, that's generally considered to be false. There is a Coriolis effect that's present, but other factors are generally thought to be what makes water go down drains, because the effect over the size of a drain is so small. Another famous story is that the Coriolis effect played an important role in a battle in the First World War. At the Battle of the Falkland Islands, there was an engagement between British and German ships, and the British had the superior force. The Germans were trying to get away. The British were shooting at long range. And the claim is that because of the Coriolis effect, the British were missing by 100 yards. Now, the idea is that the British did know about the Coriolis effect, and they had built a compensator into their calculation devices for shooting the guns. But they forgot that in the southern hemisphere, the effect is reversed. And so therefore, they were shooting off by double what the Coriolis effect should be. It's a very good story. There's nothing better than bumbling British people doing stupid things, okay? It's just a great story to have dumb British gun designers messing up at what they were doing, okay? However, it turns out not to be true. If you go and look at the records from that time, from stories about the battle reported by people who were there, they don't say anything about this happening, okay? Furthermore, the standard story is the British were surprised by this effect because they had not engaged in a battle before. But it turns out that one of the ships in this battle, I think the Glasgow here, had actually fought off the coast of Chile about 2 months earlier, and was one of several, part of a British squadron that was badly beaten by the Germans. So they would have known. This is not the first time they had encountered a long-range battle in the southern hemisphere. The reports, the standard physics story says that they were off by 100 yards, but the ability to aim a gun in the 1914 in a tossing Pacific Ocean, moving at high speed, at long range, was not that good. And in fact, the reports from the time described that if you fired a salvo of 4 or 5 shells and they all landed within a couple of 100 yards of each other, 5 miles away, that was considered good shooting. So if that is good shooting, then an effect of 50 yards doubled to 100 yards from the Coriolis effect would not be significant. So this is a bogus story. Nevertheless, it shows up in all sorts of physics books. And so you may encounter this story in your physics books. Halliday and Resnick and Crane, Physics, famous book, widely used. Kirkpatrick and Francis, Physics, A Conceptual Worldview. Walker, The Science Flying Circus of Physics. These are all sort of standard general classroom books at different levels. But even in more advanced books, this is The Foundations of Classical Mechanics. It is published by Cambridge University Press. That's generally considered a very good press. And here we have the Falkland Islands. Despite aiming well, the British shots landed about 100 meters to the left of their intended targets due to the Coriolis effect. So it's being stated here. And I hate to tell you, but it's not just in English textbooks. Here we have it. I found it in Spanish as well, okay, in a Spanish language physics text. So this is a myth. But myths are part of this Coriolis business, as we shall see. So who first thought up this effect, and who first overestimated it in canons, just like we see here in physics textbooks? Well, it's not Mr. Coriolis. Mr. Coriolis was a Frenchman who lived in the 19th century and worked out the detailed math of the Coriolis effect. And that's somehow his name got attached to it. But the person who first thought up this effect and first overestimated it was Jesuit astronomers 200 years before Coriolis in the 17th century. Now, there's something to be, this ties in with the debate over whether Earth moves, okay? As you can guess, this is an effect caused by the spinning of the Earth. If the Earth doesn't move, step back. If the Earth doesn't move, you should get a straight path on the surface of the Earth. If the Earth does move, you get a curved path on the surface of the Earth. So, one of the common mistakes that is made in discussing the whole issue of whether the Earth moved. Galileo, Jesuit astronomers in the 17th century, is the idea that the telescope showed that the Earth went around the sun. Okay, that is incorrect. Okay, there is nothing that you could see in a telescope of the 17th century that would tell you whether the Earth was going around the sun or not. The telescope did show that old ideas such as those of Ptolemy were wrong. Okay, but it did not show that the Earth moved, because before any of these Jesuits astronomers were working, a man named Tycho Brahe, right here, created his own hypothesis for the motion of the Earth, in which the Earth was at the. He liked some things about the old system of the ancients. He liked some things about Copernicus, and he sort of picked the best of both and put them together. And so he has the Earth at the center, the moon, the sun, and the stars circle the Earth, and the planets circle the sun. And so therefore discoveries like the phases of Venus, which Galileo saw with the telescope, that showed that it orbited the sun. Okay, that orbits the sun in Copernicus' system, and it orbits the sun in Tycho Brahe's as well. Galileo's discovery that moons go around Jupiter, well, in Copernicus' system, things go around other things, which would make that observation seem compatible with Copernicus. But in Tycho Brahe's system, things go around other things as well. So Tycho Brahe said that his system was fully compatible with it was fully compatible. Tycho Brahe died before the telescope was invented. But it was fully compatible with all telescopic discoveries. Tycho Brahe said that his idea was compatible with physics, because at the time there was not a physics to explain how the Earth would go. Okay, it's how do you move the Earth? The Earth is very heavy. It's made of rock. We know that. You don't have to guess what the Earth is made of. You don't have to guess at how big it is. It's a ball of rock 25,000 miles around. How do you move a 25,000-mile ball of rock? The physics was not available in the early 17th century. It's Isaac Newton who comes up with the physics for that. In the early 17th century, the idea was heavy things were hard to move. Okay, and if you say, well, what about the sun? The sun is made of something different. Okay, we come up with this in modern science. It's called dark energy, dark matter. Okay, if we don't know what something is made out of, we make up an idea for it. In the 17th century, it was called the fifth element. They assumed the celestial objects were made of something different that was very light and easy to move. And then, of course, the other thing is this was compatible with scriptural references that spoke of the Earth as being fixed. Okay. Do not believe that there were people who were like, no, I will not listen because the Bible says the Earth doesn't move, and because the Bible says the Earth doesn't move, I will not think anything else. That is not the way that people looked at it, all right? But they put a very high value on what the Bible said. And so if you were going to, it was easy enough, you could easily say, well, the Bible says that the sun rises and sets, and guess what? That's what we see. The sun rise, we see the sun set, and it's writing to how we see it, okay? But nevertheless, traditional interpretations were not going to be altered if you did not have proof, something solid, that said that the Earth moved. So, Galileo makes his discoveries, telescopic discoveries, starting in 1609 and 1610. This is Father Christoph Scheiner of the Society of Jesus. In 1614, he wrote a book called Mathematical Disquisitions, that talked all about the things that had been discovered in the heavens and his own ideas about them. One of the things that Scheiner said is, look, if the Earth rotates, then how do things fall straight down? Okay, he said, now the Earth is on an axis this way. This is like the North Pole, this is the South Pole. So the Earth is spinning like this. And he says, if everything is going to fall straight down, then what keeps it over the same spot? He said, everyone agrees that things fall straight down. So what keeps objects from over the same spot? When, he says, over the equator, an object falling above the equator will fall down while circling like this. An object at the pole will fall down straight. And an object somewhere between the equator and the pole will, if it's falling from a great height, if it is to stay above the same spot over the Earth and fall straight down, it will have to sweep out a cone as it descends like this. It's because it's going while falling in. He says, if it's to fall straight down. I mean, the contrary is that, well, if the Earth is rotating, then objects don't fall straight down. But we see objects fall straight down, so therefore, guess what? Earth must not be rotating. This is Father Giovanni Battista Riccioli. And in 1651, he elaborated on this idea more. Okay. He said, imagine that you have a cannon firing a ball to the north. Okay. If you fire the cannon to the east, okay, so here's the cannon, it shoots the ball out. If the Earth is moving this way, he says, then the cannon will move and the ball will move with it. And so if you shoot the cannon at the target B, both will move. The cannon will move from here to here. The target will move from here to here. And in the process, the ball will follow in a straight line and hit the target there. But he said if you point it north, the speed of the ground is not the same north as it is where you are. So he says if the cannon is pointed north to this target, the cannon moves from here to here. The target moves from here to here, but the ball does not follow a straight line. Like if it was all moving together, he said because of the differing speeds, the ball follows a curved path, right? Which is what we recognize. This is a discussion of the Coriolis effect. Now, Father Riccioli said, look, our cannoneers are so good, it is known that our gunners are good enough that if they aim a cannon at an enemy cannon, they can fire that cannonball such that it will go right down the mouth of the enemy cannon. And so, if they have that kind of precision in their ability to shoot, then they would have noticed this effect, because they would notice that if they were firing to the east or the west, their shots were less affected than if they fired to the north or the south. Now, that was bogus, okay, wrong. But people at that time all had the idea, well, not all, but many of them had the idea that gunners were just unbelievably accurate. And there were stories that people had, among scientists who would report that gunners knew how to aim a cannon straight up, just the right way, and shoot the ball up into the air and then have it fall straight back into the mouth of the cannon. They thought that this was an accepted idea. Well, maybe they read it in some textbook somewhere, because even today, we get these kinds of crazy ideas about guns and accuracy and stuff that appeal to people. They're stories people like, and they get repeated from one book to another. But Riccioli is the first person to do this. He cites up to back up his ideas that the gunners are accurate enough because they could shoot right into the mouth of an enemy cannon that they would have discovered this effect if it actually existed. He says, it does not exist, therefore Earth does not move. Now, this is Father Claude Francois Millet de Chales, 1674. He produces diagrams that could be used in modern textbooks today. He says, here's a tower on the Earth is rotating this way. He said, if the Earth rotates, then the top of the tower moves faster than the bottom of the tower. So as the Earth rotates, the top is carried, if you have a ball here, the top of the tower is carried from here to here, which is further than the bottom, which moves from here to here. So the ball, if you let it go, will fall, but it will not fall to I, it will fall to L. So the ball must bend as it falls and not fall straight down. He also said that he gave a simpler diagram than Riccioli. He said if you aim a cannon to the north, if the cannon is nearer to the equator, it will be carried further as the Earth rotates than the target. So as the cannon is carried to the east, the target is carried to the east less, and so you fire the cannonball to the target, the ball will end up missing the target to the east. That's that Coriolis deflection. This diagram is pretty much exactly what you might find in a standard meteorology or physics textbook today. Now, the fact of the matter is that the Coriolis effect is actually very hard to detect. Okay, they could not detect it in falling balls and cannon shots because of ideas that we have in physics today. We understand something called turbulence, that when something is sent moving at a speed, it develops a wake of swirling air behind it, which can produce strange effects on the ball. In baseball, spin will stabilize a pitch, but if a pitcher throws what's called a knuckleball, I wish I knew the Spanish term for a knuckleball, but they throw it so the ball hardly spins at all. Hey, Jerry, do you know this Spanish word for knuckleball? I don't think so. Okay. So, but the ball, when it tends to wobble in flight, okay, from the turbulence behind it. It's very hard to drop objects in the exact same place over and over again. So people would experiment in high towers and would drop objects, and they would think, well, I'm dropping a heavy lead ball, it should fall straight down, or if there's a deflection, it should deflect, and we should be able to measure it. In fact, they found the balls went all over the place. In fact, there were stories of trying to do this in deep mines in England that are thousands of feet deep, and they let the ball go at the top, and they never find, and the ball would disappear. Okay, it didn't disappear, of course, but it got going so fast and got off track so much that it buried itself in the wall of the mine, and somewhere at the 2,000-foot level, and you just never found it. Eventually, the Coriolis effect was discovered, and it was demonstrated in pendulums. So if you've been to a museum, typically, that has a swinging pendulum that changes its angle over the course of a day, that's a Coriolis effect demonstration. They talk about it being a demonstration of the rotation of the Earth, which it is. But the idea is that if a shot to the north deflects east and a shot to the west, to the south deflects west, then if you set that pendulum swinging back and forth, north to south, every north swing will deflect a little bit to the east. Every south swing will deflect a little bit to the west. It's very tiny, but with doing it over and over and over and over again, it adds up and it turns the plane of the pendulum. And this is called a Foucault pendulum, after Foucault, who in 1851 demonstrated it in February in the Pantheon in Paris. But Father Angelo Secchi did it at the Church of St. Ignatius in Rome in May of 1851, and because he wanted to replicate Foucault's results. And so he successfully strung up a very long cable in the church and swung a pendulum and demonstrated the Coriolis effect. It wasn't called the Coriolis effect yet at that time. Now, interesting thing about Father Secchi is he then went on to build a whole observatory atop the Church of St. Ignatius in Rome. The Church of St. Ignatius was built in order to have a dome on it, a big dome. They must have run out of money because they did not build a dome. They built a flat, just a regular roof. But because they had built the church to have this big dome, it had these very strong pillars in its structure. And so Father Secchi thought those pillars are so strong they could be the stable base for an observatory. And he put a telescope on top, a whole observatory on top of St. Ignatius in Rome. Father Secchi was a pioneer in the use of spectroscopy, using a prism to break the light from the stars and sun and whatnot into a spectrum that could then be analyzed to classify them and later determine what chemicals were present in them and things of that nature. And of course, spectroscopy is used in all sorts of science today. Secchi is not the only pioneer in spectroscopy. William and Margaret Huggins are also pioneers, but Secchi and the two Hugginses are sort of the main ones. So this is a diagram of his observatory at the, arrow. This is a diagram of his observatory atop the church. This is the church, a diagram of the church seen from inside. There's the observatory. You can actually see the ruins of his observatory on Google. If you go to Google and you look for Chiesa di Sant'Ignazio di Loyola, and in Rome, here's the church. Here it is, and if you look, there is a little curve. That is part of where they were going to put the big dome on top of it. They did not, and this is Father Secchi's observatory dome. The dome's gone, but the base of it is still there. This was of course, in 1651. But that's up closer. Here you can see the structure to support the big church dome that was never built here. Okay, so there's going to be a big dome here. They just put a regular roof on it. And right here is this. Okay, so this is the pier to hold the big telescope. That's right there. And then the dome, which is along here. And the wooden dome, of course, is gone. Next Jesuit and the Coriolis effect, Father Johann Georg Hagen in 1910. Father Hagen was interested in proofs of the Earth's rotation. Why, I don't know, okay, but he found this an interesting thing to study. And he set up a couple of special experiments within the Vatican to do this. So this was in the basement of one of the domes, and I'll show you where the domes were at that time. And this hangs on two cords and has two heavy, I think 100 kilogram lead masses, which would then roll out. He had a mechanism which would make them roll to either side, and that would be to send an object, and then there would be a Coriolis effect on it to deflect it, and the deflection would cause the whole arm to move, and then there's a light and a mirror to reflect onto this scale to detect the deflection of the beam as the carts moved out. This is the only experiment other than Foucault's pendulum that could reliably show the Earth's rotation. So here's the Vatican, and here's where the Vatican Observatory was in the early 20th century. You can see this is, of course, the Vatican and St. Peter's Dome, and there's an observatory dome. There's one, and there's one. There's also another one over here, but it's harder to see, more difficult. There you can see this picture here. That is this section. So that building is this building. This wall is this wall. And there's the dome. And there's the dome. And the Coriolis effect, which he called the isotomeographeo, was down in the bottom of this dome, or maybe it was in the bottom of this. I'm not sure which, but it was in one of those two towers, round towers. And that round tower then made for the round room that's in. Father Hagen also created a second experiment in one of the stairwells of the Vatican that was about 75 feet down, where he dropped objects. But instead of dropping them and just letting them fall, he got around the problem of air turbulence by using what's called an Atwood machine, which has a counterweight so that the object drops more slowly. So it's got a counterweight on the other side, and the two things go like this. And that way the object fell slowly. And he built this telescope. Actually, he had this telescope made to look down as the object fell, and so that as the object fell and the Earth rotated underneath the object, he could measure its deflection. And I think he was able to measure it to 1% accuracy. So these are all Jesuits who have investigated or studied the Coriolis effect. And the first Jesuits, so Hagen and Secchi, both studied it after the effect had been confirmed, but Scheiner, Riccioli, and Deschales were all before anyone had ever thought up of the effect itself. And Scheiner, Riccioli, and Deschales all looked at this as proof that the Earth was not turning. Okay, because they said this effect should exist. If Earth turns, this effect should exist. We don't see this effect, therefore the Earth does not turn. Therefore Copernicus and Galileo and such are wrong. Turns out the effect does exist. It was just harder to detect than they thought. So they were right about the effect, wrong about it not existing. Nevertheless, there's some broader points to take away from the question of the Society of Jesus, the rotation of the Earth, and the Coriolis effect. Okay, and one of these is beware stereotypes about who does science and who doesn't do science. Okay, there is a stereotype, okay, you know, the idea, this is a cartoon, you know, where Galileo is telling the churchman about his discoveries with the telescope, and the churchman is thinking about bashing Galileo over the head with the telescope, okay? Now, that's the stereotype, okay? But in fact, Father Scheiner, and he is not the only one, but he's the one that I'm talking about. He's not the only Jesuit to be doing astronomy. These are all his works, all his stuff. This is the diagram I told you about. But the churchman who doesn't want to think about looking at the moon, here is his diagram of the moon, right? Here is his diagram of the system of Jupiter, showing Jupiter, its satellites, its shadow, the points at which the satellites go in and out of the shadow, the points at which the satellite go in front of and come out from in front of the disk of Jupiter, the various radii of the orbits, angles that you should measure, because he believed that you could use timing of the orbits of Jupiter to measure out the size of the solar system through trigonometry, okay? He felt that this should be really closely studied. The phases of Venus as it goes around the sun, okay? And sunspots. Scheiner is the most significant, he is the first astronomer to seriously study anything in the sky. Okay, by seriously study, I don't mean point the telescope and see something new and say, oh, cool, look what I've discovered. But I mean more like what modern astronomers do, which is to seriously, you know, dedicate years of time to studying an object and learning everything that they could learn about it. Not, oh, look at that and move on to something else, but rather a deep treatment of it. He spent years doing solar observations, and this is one of his diagrams of the sun and sunspots. You may not be able to see it, but every darn sun, every sun that he has in there, it's got the Jesuit logo on it. Every one. So he has that on the sun everywhere. So the stereotype is the guy not wanting to look through the telescope. The reality is the guy looking at everything through the telescope. Father Scheiner did not believe that the Earth moved. You can't see it here. I cut it out on purpose, but the Earth is here, and this is the sun, and that is the sun's orbit as it went around the Earth, because Father Scheiner ascribed to Tycho Brahe's system of the universe. The stereotype, what this has to do to the broader point, is that the stereotype is what we think of as people in science is we think of people like Einstein and Darwin, okay, which are a certain type of people, okay. In fact, other people did science. Of course, this is Secchi. These are oh gosh, I've blanked on their names. Only one I can remember is Regina. But anyhow, these are 3 nuns who worked on a Vatican Observatory stellar charting project in the early 20th century. Before, has anyone ever seen the movie Hidden Figures? Okay. Well, think of something very similar. That in the Hidden Figures movies, the women were doing work, they were doing calculations. Eventually, they stopped doing those because people developed electronic computers. They were doing measurements and stuff that, and of course, today we would have a computer do, but their measurements were key to making this project work. And then I found some other pictures of people here doing astronomy. Okay, so I just found those off the internet. So in reality, lots of different people have contributed to astronomy. Okay, not just people like Einstein and Darwin. Guys with long white beards. Galileo would be in there too. And so it illustrates when you look more deeply into science's history, how many different sorts of people were involved in science. All right, and so that is the end. And we have time, I think, for questions. So.
Si hay alguna pregunta, por favor me indican para pasarles el micrófono. Está siendo transmitida la conferencia. If there is any question, please let me know to pass you the microphone. Well, before someone appears, I want to ask you a question. How did the Jesuits convince the Pope to give them money for their experiments? What kind of reasons did they expose to the Pope, for example, to do these kind of rotation experiments?
So, of the Jesuits here, none of them, except for maybe Hagen, because Scheiner was in Germany, Riccioli was in Bologna, and Deschales was in Belgium. So they were all, of course, the Society of Jesus was widely dispersed. Secchi, his observatory belonged to the Collegio Romano, the Jesuit college in Rome. So only Hagen would be directly supported by the Pope. And by that time, Hagen was the director of the Vatican Observatory at that time. The Vatican Observatory was not originally under Jesuits. It was originally, I can't remember, who the first couple directors were not Jesuits, but then the Pope was not happy with the person who was running it. They weren't getting the star mapping project done. And that was, the Pope had been stripped of his territory in the 19th century, and they wanted the observatory to be significant, to say, hey, look, we still exist as an entity, we're contributing to international science. So he asked one of the bishops that he knew in Italy to look for a really good scientist to take over the observatory, and they got Hagen. And so Hagen was then the person. And I think, his experiments didn't cost a lot of money. It's not. It was so. The Vatican Observatory has a budget. It's supported by the Vatican City-State, and it's supported about the same way as NASA is supported by the U.S. government. In other words, that the amount of the U.S. government that goes to NASA is on 1% or something like that, and the amount of the Vatican City-State government that goes to the Vatican Observatory is about 1%. But of course, the Vatican City-State government is not nearly so big as the United States government's budget. And so, it's not, in strict terms, it's not that much. Most of the money ultimately comes from tourism. So, of the money that, is in the Vatican's budget, about, I don't know this, don't quote me on this, I'm making, I sort of remember, but about 20% comes from, your Peters Pence collections and those kinds of things. 80% of it comes from tourists coming into the Vatican museums. There's tons and tons and tons of tourists. It's just incredible. If you've ever been there, it's just huge amounts of tourists. And to make sure that the Vatican Observatory helps with that, just this past year, it really started during the COVID shutdown. They turned a couple of the old telescope domes into a visitor center. So the telescopes were not being used because they're older. There's one of them that would be a good telescope if it was in a dark sky place, but Brother Guy says it would cost more to move the telescope than it would be to build a new telescope. So the telescopes that are there are used either for public viewing or not at all. So it's perfectly happy to have people come tour it, so they got it all fancied up and made displays, and now you can go on a tour of the Papal Gardens and make a stop at the Vatican Observatory's historic telescopes. So, and Brother Guy says, always be happy if you see them there because they're paying the bills.
I have two questions. The first one is Saki introduced this way of study the sky with a
Spectrography, yeah.
How was possible at that time using this tool?
So it started with in chemistry, that people began burning metals in a candle flame and noticing that it changed the flame color, and they passed the light through a prism, a glass prism, and then somebody got the idea. I think it was Huggins. It wasn't. I don't think Secchi came up with the idea. I think Huggins or someone else came up with the idea. Pass starlight through a prism and see what happens. And from that, they could see the same patterns in the light of stars that you saw in the light on Earth from chemicals. It was very interesting because in that same time, a French philosopher named, I think it's Auguste Comte, had said, science will never know what stars are made of. You will never know the composition of a star. And within 10 years, we were knowing what the composition of stars were because we looked at it and see the same pattern in the light through spectroscopy. And Father Secchi began classifying stars by their spectrum, saying, hey, these stars have similar spectra. These stars have similar spectra. And now astronomers classify stars by spectra all the time.
Thank you. And the last question is, right now, there is a group there in the Vatican Observatory in the Vatican. There exists a group that uses the telescope to say that in the Vatican it's public, only fathers.
So the telescopes that are in the Vatican or that are at Castel Gandolfo to the south, all those telescopes on the wall that you saw in this picture, they were all moved to Castel Gandolfo. So the Castel Gandolfo is 30 miles, 40 kilometers south of Rome, to get away from the light of Rome. But now none of those are used for scientific research, only the one at Mount Graham in Arizona. And yes, there is the director, who's a Jesuit. There are resident astronomers, people who live at the observatory. Those are all Jesuits that live in the community, in a community. And then there are people like me who are not Jesuits, who, some of them are full-time employees, present, secretary, all sorts of, just regular staff members. And then also people who, like me, I mostly do my work, remotely. And so, I only go to the observatory, quite rarely, really. And so most of my stuff is done, like many people in science, and you're doing stuff, with information stuff shared electronically. And so there's a large number of people who are not Jesuits not residents who work with the observatory too.
Thank you.
There was.
So, okay. So I was just wondering, what other like phenomena are affected by the Coriolis effect? Like, you gave us the example like hurricanes, but I don't know if, for example, light is affected by it or something else.
I have to think about light. Light is different because its speed is not affected by the motion of an observer. So I'd have to think about that. I think light, there would be some sort of Coriolis, some sort of effect of motion, but you'd have to apply relativity to it. So it is true that long-range shots with rifles have a Coriolis effect. But mostly it's in ocean and atmospheric stuff, and therefore planetary atmospheres as well. Okay, so Jupiter, fast rotating, many cyclones. Venus, slow rotating, not many cyclones. But ocean currents also, anytime you have a large amount of material moving across the surface of a rotating planet, it will be deflected by the Coriolis effect. And then, of course, if they want to do space launches and things like that, you have to incorporate the motion of the Earth into that as well. So you'll get a Coriolis effect if you want to put a rocket up into orbit. You have to think about, but they might not call it Coriolis effect because they're looking at it from such a big scale. But the motion of the Earth is going to play a part in it. So, and then amusement park rides. If you've been on spinning amusement park rides and you try tossing something, things like you'll see, they'll do all kinds of like the picture of the woman with the merry-go-round, the carousel.
Why did you think it was important to delve into the study of the Jesuits in astronomy and into the crossover between history, religion, astronomy, and science? I have two more.
Can I answer your first one first? Let me answer your first. What you have, because my students asked me about it. I taught for 30 years. But I retired from being mostly teaching at a college, and during that time, so this is before I worked for the VO, for the Vatican Observatory. And I would teach an astronomy class, and we would get to the question of, having to change from thinking that the Earth stands still to thinking that the Earth turns, and people would read this, they would read discussions that went like this. And they would say, and I had students who would ask me, why would someone be so stupid as to not pay attention to Galileo? Why would anyone be so stupid as to say, a guy said to me, why would somebody say that because a church person tells me the sky is pink, that I will believe that because the Bible says the sky is pink? Why would I believe that if the sky was blue? And I hadn't thought about it that much. I did astronomy. And I began looking. I was like, well, why is that? And I taught, I won't go into a lot of detail, but many of the students I taught had not come through the best education systems. And so they did not necessarily trust, authority. I went through a pretty good education system, and basically if my professor said it, I was like, yeah, I believe that, Whereas these guys were more like, teaching in schools haven't done much good for me. I don't necessarily believe what professors say. So they would ask me a lot of hard questions. And so I started looking like, well, why would somebody say that? And the answer is they didn't. The answer is this is wrong. But I had to look as to what was the evidence for Earth's rotation? Why would you not believe Earth was rotating? And so on and so forth. And it becomes pretty straightforward. You can easily understand why they thought the Earth wouldn't rotate from a scientific perspective. There's problems with physics. There's a Coriolis effect. There's some issues involving the stars. And there was actually a very you would not have, if you were a scientist in 1630, you would not have believed Galileo either. You would have believed the Jesuits, you know, so. Now, what was your other questions?
Second one is, what can or should be done from universities such as ITESO in order to educate new professionals into science?
Oh, I think that's more than I can answer, you know.
I'll go to the third one then.
Okay. I tell you what, I will tell you this. You know, there's two things that's very difficult everyone generally agrees we need more people in science, and we need a broader variety of people in science. And there's two things. One is there's people who come into school. So I taught many students who had been through poor schools. If you've been through a poor school, it doesn't mean you're stupid, okay? It means you've been through a poor school. And there's a problem in science that we will tend to say, oh, these people, they can't do math, they're not as good, they shouldn't be scientists. That's not necessarily true. You have to give them a chance and, you know, give them a chance to catch up. They may be very smart and catch up and learn math. And it's generally been shown that if you give people a year or two, if they have the ability, they'll catch up even if they went to a bad school. So that's one thing. And then the other thing is, though, is you can't use that as an excuse to say, well, nobody needs to know anything. We want to let everyone through to be fair. So we're not going to ask anything. And so I think those are two things you have to both be broad in letting people in and giving them chances to succeed while not making your curriculum weak. So, okay.
The third one, you kind of already answered it, but I'm just going to say it anyways. What do you think comes out from the reflection between philosophical and theological theories arising from the observation of the sky? How do you think they complement each other?
That's a long question. I'll just say this much. This has been going on for a really long time. One of the things that in my research, did you know that St. Augustine discussed this in when did St. Augustine? 4th century. In Genesis, it says in the first chapter, it says God. It's the 4th day of creation. It talks about God makes the sky. He says, and He puts lights in the heavens, and He says 2 great lights. The greater light to rule the day, the lesser light to rule the night, and then the stars. Okay, fine. If you think that the sky is a dome, and these are lights on it, that makes sense. You look at the stars, they look smaller, they are smaller. But by the time of St. Augustine, astronomers had figured out how to measure, not the distance to the stars, but at least know how the minimum distance to the stars, by measuring from different places on the Earth's surface and using something called parallax. And they had already figured out that the stars had to be far more distant than the sun and the moon. Okay, you know the sun has to be more distant than the moon in an eclipse. The sun is behind the moon. So the sun must be, they both look about the same size, so the sun must be bigger than the moon. Well, the stars were really far away, and if you look at what size the stars appear and work out that with the distance, they must be bigger than the moon. And so even as early as Augustine is like, hey, science shows that this Bible says the stars are the sun and moon are the 2 great lights, but science shows that the stars are greater than the moon. What are you going to do about that, religion and science? And you know what everybody said? Who cares, right? It's obvious the Bible is talking about the stars do look smaller than the moon, and that is what the Bible is speaking to us. It is not giving us a science lesson on the dimensions of celestial bodies. And that is, that has largely been forgotten, but it's in Augustine, it's in Thomas Aquinas, it's in John Calvin. And John Calvin goes on, he's the most fun to read on this because he goes on and on about how great astronomy is and how smart astronomers are, even as he's talking about how astronomy contradicts the Bible. But he's saying that's because the Bible is written for what we see, And so this can be done. This can be worked. This is not, it's been dealt with for almost 2,000 years.
Thank you, Chris. I want to make an announcement. Chris will be at the library giving 2 more lectures about these subjects. So please, I want to invite you to go with Chris talk with Chris about these very interesting subjects and take advance of his visit. So I think it's important to do this announce, to give you this announce right now. No? Can you tell us about the next two talks are you going to give us in the library, and maybe they will be interesting
so
to
we had talked about, are we going to have an observing session with the telescopes?
I hope so. Tomorrow, Wednesday, it depends about the weather.
Right.
The problem is the weather. We are very good, but not controlling the weather yet. So
okay. So the idea is that the moon and Jupiter are both visible, and that we could see with a telescope. And so I would talk to Professor Javier, and that I would do one talk on Jesuits and their observations of the moon, and another talk on Jesuits and their observations of Jupiter. And those are related to, if you come to those, you will see, where is it? Oh, went the wrong way. Things like more discussion about like this, and how if you followed science in the 17th century, you would have to conclude that the moon is translucent and light passes through it. So, very interesting stuff.
I think there is another question. If not, another one? Okay, yeah.
So I have two questions. The first one is, how do scientists study and measure this effect on the Earth's oceans and atmospheres? Like, is it different? Does it have a different effect, whether it's in like the water or is it up in the air?
No, it's pretty much the same effect. In the air, in the water, is the same way. In other words, a ocean current moving to the south will be deflected toward the west. One moving to the north will be deflected toward the east. And so the mechanism works the same regardless of what it is that's moving. So air, water, projectiles. There's even evidence that rivers that flow to the north, that flow northward, have a tendency to erode their eastern banks a little more because of the deflection of them flow to the north. They would deflect to the east, erode their western banks. This is sort of disputed, but there are claims that you can actually measure this. So.
Okay, and the second question is, you mentioned in your presentation that, there's like other celestial bodies like planets and stuff that have this effect. Are there any other type of celestial bodies like, I don't know, wormholes or stars that have this effect, and how is it different?
So wormholes are a theoretical object, so we don't know that actually exists. So, but stars, so stars, a star is complicated because it doesn't rotate. The sun does not rotate like the Earth does. The sun rotates, but it does not. So the Earth rotates as a solid. The whole thing, everything rotates at the same speed. So everything takes 24 hours to go around to everybody on Earth. If we lived on the sun, that wouldn't be true. The equator goes around faster than the poles because the sun is a fluid. And so that would make whatever Coriolis effects you would have really crazy. Jerry, do you know, I want to say that there are vortices on the sun. I don't know if they're, I would presume that they are influenced by a Coriolis type process. It's a simple process, so anything that's going to rotate will have it, but on a differentially rotating object like the sun, it would be really complicated. Yeah. Yeah. And then especially cooler stars, have atmosphere. They're the boundary between a planet and a star is not real clear. So if you keep making a planet bigger, its behavior becomes more star-like. Or if you make a star, its planet behavior so this border we call brown dwarfs. And so they have atmospheres. They'll have, we expect that they would have appearances somewhat similar to Jupiter, and therefore might have star storms, but we don't have any imaging of we don't have any imaging of a brown dwarf, do we, Jerry, that you know of? But I mean, no, we can't resolve them. Yeah. So.
Okay, thank you. And just by the way, you have a really cool tie.
This tie has been a big hit. I've got more comments on this tie today. They're all positive, so thank you.
Where did you buy?
I didn't. I think someone gave it to me as a present, I think.
At the Vatican store or what?
I do not have this good of taste. So.
Well, another question, yeah. The thing is, okay.
And another question came to my mind when we talk about celestial bodies, and is that, is the Coriolis effect present when we talk about like gravitational pull or force in celestial bodies? And if so, as an example, is working on light when we talk about gravitational pull?
So you do not need the gravitational pull for the Coriolis effect. So like, in here, gravity's not playing a role here, other than holding the ball on the disk. But if you are in a rotating space station, in deep space where there's no gravity, there would still be the Coriolis effect from that. So where you might get like a combination of the two would just be in a falling object. So an object falling in. But the object itself, it would be more like if you launch an object up from a rotating body, then you're going to involve the Coriolis effect for that rising object. It's going to deflect, right? Or if you drop something from a tower attached to the object, of course, that too. But towers don't get that tall, so you're mostly, if you want like to try to imagine, like an extreme circumstance would be like on a pulsar, strong gravity, rapid rotation, and then we imagine something, smashing into the pulsar and kicking up a piece of debris out of that. And then you would have fast rotation, strong gravity, rising objects. You would probably get some really crazy Coriolis effect there. Yeah, but the Coriolis effect itself is actually very, sort of very simple. You're welcome.
Thank you very much for coming. I think because the time, because Jerry will give us the next conference. Jerry, the next conference will be in Spanish or English? Okay, so before the vote has done, let me give Chris. Thank you very much for your lecture. Applause, please. And I will give him, in the name of the Departamento de Matemáticas y Física and in the name of Directora General Académica, because the academic I want to give Chris a gift, and first a certificate of the conference. Thank you very much. And a present from the Dirección General Académica. Give us this present for our guests. Thank you very much, Chris, for being here. Thank you very much. And thank you very much all for coming. And Jerry, We will have maybe 30 minutes of a break. Los que quieran acompañarnos en la siguiente plática, va a estar Jerry con nosotros. Les invito a quedarse, ir y regresar. Va a haber diferentes actividades todavía. Y Jerry va a tener la siguiente en más o menos 6:10 empezamos aproximadamente, ¿no? Gracias a todos por venir, muchas gracias.